Some basic concepts of chemistry. Chemistry is the science of molecules and their transformations. It is the science not so much of the 100 elements but of the infinite variety of molecules that may be built from them. Roald Hoffmann. Science can be viewed as a continuing human effort to systematize knowledge for describing and understanding nature. You have learned in your previous classes that we come across diverse substances present in nature and changes in them in daily life. Curd formation from milk, formation of vinegar from sugarcane, juice on keeping for prolonged time and rusting of iron are some of the examples of changes which we come across many times. For the sake of convenience, science is subdivided into various disciplines: chemistry, physics, biology, geology, etc. The branch of science that studies the preparation, properties, structure, and reactions of material substances is called chemistry. Development of chemistry. Chemistry as we understood it today is not a very old discipline. Chemistry was not studied for its own sake. Rather, it came up as a result of search for two interesting things. Number one, philosopher's stone, Paris, which would convert all baser metals, example iron and copper, into gold. Number two, elixir of life, which would grant immortality. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied that knowledge in various walks of the life. Chemistry developed mainly in the form of alchemy and iatrochemistry during 1300 to 1600 CE. Modern chemistry took shape in the 18th century Europe after a few centuries of alchemical traditions which were introduced in Europe by the Arabs. Other cultures, especially the Chinese and the Indian, had their own alchemical traditions. These included much knowledge of chemical processes and techniques. In ancient India, chemistry was called Rasayan Shastra, Rasatantra, Raskriya or Rasavidya. It included metallurgy, medicine, manufacture of cosmetics, glass, dyes, etc. Systematic excavation at Mohenjo-daro in Sindh and Harappa in Punjab proved that the story of development of chemistry in India is very old. Archaeological findings show that baked bricks were used in construction work. It shows the mass production of pottery, which can be regarded as the earliest chemical process, in which materials were mixed, molded, and subjected to heat by using fire to achieve desirable qualities. Remains of glazed pottery have been found in Mohenjo-daro. Gypsum cement has been used in the construction work. It contains lime, sand, traces of CaCO3. Harappans made faience, a sort of glass which was used in ornamental. They melted and forged a variety of objects from metals such as lead, silver, gold and copper. They improved the hardness of copper for making artifacts by using tin and arsenic. A number of glass objects were found in Maski in South India in 1000 to 900 BC and Hastinapur and Taxila in North India, that is 1000 to 200 BC. Glass and glaze were colored by addition of coloring agents like metal oxides. Copper metallurgy in India dates back to the beginning of Chalcolithic cultures in the subcontinent. There are much archaeological evidences to support the view that technologies for extraction of copper and iron were developed indigenously. According to Rigveda, tanning of leather and dyeing of cotton were practiced during 1000 to 400 BC. The golden gloss of the black polished ware of northern India could not be replicated and it is still a chemical mystery. These wares indicate the mastery with which kiln temperature could be controlled. Kautilya's Arthashastra describes the production of salt from sea. A vast number of statements and material described in the ancient Vedic literature can be shown to agree with modern scientific findings. Copper utensils, iron, gold, silver ornaments and terracotta discs and painted grey pottery have been found in many archaeological sites in North India. Sushruta Samahita explains the importance of alkalis. The Charaka Samahita mentions ancient Indians who knew how to prepare sulfuric acid, nitric acid, and oxides of copper, tin, and zinc. The sulfates of copper, zinc, and iron are the carbonates of lead and iron. Rasopnishada describes the preparation of gunpowder mixture. Tamil text also describe the preparation of fireworks using sulfur charcoal, saltpetre, that is potassium nitrate, mercury, camphor, etc. Nagarjuna was a great Indian scientist. He was a reputed chemist, an alchemist, and a metallurgist. His work Ras Ratnakar deals with the formulation of mercury compounds. He has also discussed methods for the extraction of metals like gold, silver, tin, and copper. A book Rasarnavam appeared around 800 CE. It discusses the uses of various furnaces, ovens, and crucibles for different purposes. It describes the method by which metal could be identified by flame color. Chakrapani discovered mercury sulfide. The credit for inventing soap also goes to him. He used mustard oil and some alkalis as ingredients for making soap. Indians began making soap in the 18th century CE. Oil of Iranda and seeds of mahua plant and calcium carbonate were used for making soap. The paintings found on the walls of Ajanta and Ellora, which look fresh even after ages, testify to a high level of science achieved in ancient India. Varahamihir in Brihat Samhita is a sort of encyclopedia which was composed in the 6th century CE. It informs about the preparation of glutinous material to be applied on walls and roof of houses and temples. It was prepared entirely from extracts of various plants, fruits, seeds, and barks, which were concentrated by boiling and then treated with various resins. It will be interesting to test such material scientifically and assess them for use. A number of classical texts like Arthveda mention some dye stuff. The material used were turmeric, madar, sunflower, orpiment, cochineal, and lac. Some other substances having tinting property were Camplesia, Patanga, and Jatuka. Varahamihir Brihat Samhita gives references to perfumes and cosmetics. Recipes for hair dyeing were made from plants like indigo and minerals like iron power, black iron or steel, and acidic extracts of sour rice gruel. Gandhayukli describes recipes for making scents, mouth perfumes, bath powders, incense, and talcum powder. Paper was known to India in the 17th century as account of Chinese traveler Ai describes. Excavation at Takshila indicate that ink was used in India from the 4th century. Colors of ink were made from chalk, red lead, and minima. It seems that the process of fermentation was well known to Indians. Vedas and Kautilya's Arthashastra mention about many types of liquors. Charaka Samhita also mentions ingredients such as barks of plants, stem, flowers, leaves, wood, cereals, fruits, and sugarcane for making aswas. The concept that matter is ultimately made of indivisible building blocks appeared in India a few centuries BCE as a part of philosophical speculations. Acharya Kanda, born in 600 BCE, originally known by the name Kashyap, was the first proponent of the atomic theory. He formulated the theory of very small indivisible particles, which he named Parmanu, comparable to atoms. He authored the text Vaishika Sutras. According to him, all substances are aggregated form of smaller units called atoms, Parmanu, which are eternal, indestructible, spherical, suprasensible, and in motion in the original state. He explained that this individual entity cannot be sensed through any human organ. Kanda added that there are variety of atoms that are as different as the different classes of substances. He said these Parmanu could form pairs or triplets. Among other combinations and unseen forces causes interactions between them. He conceptualized this theory around 2500 years before John Dalton, 1766 to 1844. Charaka Samhita is the oldest Ayurvedic epic of India. It describes the treatment of diseases. The concept of reduction of particle size of metals is clearly discussed in Charaka Samhita. Extreme reduction of particle size is termed as nanotechnology. Charaka Samhita describes the use of bhasma of metals in the treatment of ailments. Nowadays, it has been proved that bhasmas have nanoparticles of metals. After the decline of alchemy, iatrochemistry reached a steady state, but it too declined due to the introduction and practice of Western medical system in the 20th century. During this period of stagnation, pharmaceutical industry based on Ayurveda continued to exist, but it too declined gradually. It took about 100 to 150 years for Indians to learn and adopt new techniques. During this time, foreign products poured in. As a result, indigenous traditional techniques gradually declined. Modern science appeared in Indian scene in the later part of the 19th century. By the mid-19th century, European scientists started coming to India and modern chemistry started growing. From the above discussion, you have learned that chemistry deals with the composition, structure, properties and interaction of matter and is of much use to human beings in daily life. These aspects can be best described and understood in terms of basic constituents of matter that are atoms and molecules. That is why chemistry is also called the science of atoms and molecules. Can we see, weigh and perceive these entities? Is it possible to count the number of atoms and molecules in a given mass of matter and have a quantitative relationship between the mass and the number of these particles? We will get the answer of some of these questions in this unit. We will further describe how physical properties of matter can be quantitatively described using numerical values with suitable units. 1.1 Importance of chemistry. Chemistry plays a central role in science and is often intertwined with other branches of science. Principles of chemistry are applicable in diverse areas such as weather patterns, functioning of brain and operation of computer, production in chemical industries, manufacturing fertilizers, alkalis, acids, salts, dyes, polymers, drugs, soaps, detergents, metals, alloys, etc., including new material. Chemistry contributes in a big way to the national economy. It also plays an important role in meeting human needs for food, healthcare products and other material aimed at improving the quality of life. This is exemplified by the large-scale production of a variety of fertilizers, improved variety of pesticides and insecticides. Chemistry provides methods for the isolation of life-saving drugs from natural sources and makes possible synthesis of such drugs. Some of these drugs are cisplatin and Taxol, which are effective in cancer therapy. The drug AZT, that is azithromycin, is used for helping its patient. Chemistry contributes to a large extent in the development and growth of nation. With a better understanding of chemical principles, it has now become possible to design and synthesize new material having a specific magnetic, electrical and optical properties. This has led to the production of superconducting ceramics, conducting polymers, optical fibers, etc. Chemistry has helped in establishing industries which manufacture utility goods like acids, alkalis, dyes, polymer, metals, etc. These industries contribute in a big way to the economy of a nation and generate employment. In recent years, chemistry has helped in dealing with some of the pressing aspects of environmental degradation with a fair degree of success. Safer alternatives to environmentally hazardous refrigerants like CFCs, chlorofluorocarbons, responsible for ozone depletion in the stratosphere, have been successfully synthesized. However, many big environmental problems continue to matters of grave concern to the chemist. One such problem is the management of the greenhouse gases like methane, carbon dioxide, etc. Understanding of biochemical processes, uses of enzymes for large-scale production of chemicals, and synthesis of new exotic material are some of the intellectual challenges for the future generation of chemists. A developing country like India needs talented and creative chemists for accepting such challenges. To be a good chemist and to accept such challenges, one needs to understand the basic concepts of chemistry, which begin with the concept of matter. Let us start with the nature of matter. 1.2 Nature of matter. You are already familiar with the term matter from your earlier classes. Anything which has mass and occupies a space is called matter. Everything around us, for example, book, pen, pencil, water, air, all living beings, etc., are composed of matter. You know that they have mass and they occupy space. Let us recall the characteristics of the states of matter which you learned in your previous classes. 1.2.1 States of matter. You are aware that matter can exist in three physical states by solid, liquid and gas. The constituent particles of matter in these three states can be represented as shown in figure 1.1. Particles are held very close to each other in solids in an orderly fashion that there is not much freedom of movement. In liquids, the particles are close to each other but they can move around. However, in gases, the particles are far apart as compared to those present in solid or liquid states, and their movement is easy and fast. Because of such arrangement of particles, different states of matter exhibits the following characteristics. Number 1. Solids have definite volume and definite shape. Number 2. Liquids have definite volume but do not have definite shape. They take the shape of the container in which they are placed. Number 3. Gases have neither definite volume nor definite shape. They completely occupy the space in the container in which they are placed. These three states of matter are interconvertible by changing the conditions of temperature and pressure. On heating, a solid usually changes to a liquid and the liquid on further heating changes to a gas. In the reverse process, a gas on cooling liquefies to the liquid and the liquid on further cooling freezes to the solid. 1.2.2 Classification of matter. In class 9th, chapter 2, you have learned that at the macroscopic or bulk level, matter can be classified as mixture or pure substance. These can be further subdivided as shown in figure 1.2. When all constituent particles of a substance are same in chemical nature, it is said to be a pure substance. A mixture contains many types of particles. A mixture contains particles of two or more pure substances which may be present in it any ratio. Hence, their composition is variable. Pure substances forming mixture are called its components. Many of the substances present around you are mixtures. For example, sugar solution in water, air, tea, etc. are all mixtures. A mixture may be homogeneous or heterogeneous. In a homogeneous mixture, the components completely mix with each other. This means particles of components of the mixture are uniformly distributed throughout the bulk of the mixture and its composition is uniform throughout. Sugar, solution and air are the example of homogeneous mixture. In contrast to this, in heterogeneous mixture, the composition is not uniform throughout and sometimes different components are visible. For example, mixtures of salt and sugars, grains and pulses along with some dirt, often stone pieces, are heterogeneous mixtures. You can think of many more examples of mixtures which you come across in the daily life. It is worthwhile to mention here that the components of a mixture can be separated by using physical methods such as simple handpicking, filtration, crystallization, distillation, etc. Pure substances have characteristics different from mixtures. Constituent particles of pure substances have fixed composition. Copper, silver, gold, water and glucose are some examples of pure substances. Glucose contains carbon, hydrogen and oxygen in a fixed ratio and its particles are of same composition. Hence, like all other pure substances, glucose has a fixed composition. Also, its constituents carbon, hydrogen and oxygen cannot be separated by simple physical methods. Pure substances can further be classified into elements and compounds. Particles of an element consist of only one type of atoms. These particles may exist as atoms or molecules. You may be familiar with atoms and molecules from the previous classes. However, you will be studying about them in detail in Unit 2. Sodium, copper, silver, hydrogen, oxygen, etc. are some examples of elements. All atoms are one type. However, the atoms of different elements are different in nature. Some elements such as sodium or copper contains atoms as their constituent particles, whereas in some others the constituent particles are molecules which are formed by two or more atoms. For example, hydrogen, nitrogen, oxygen gases consist of molecules in which two atoms combine to give their respective molecules. This is illustrated in figure 1.3. When two or more atoms of different elements combine together in a definite ratio, the molecule of a compound is obtained. Moreover, the constituents of a compound cannot be separated into simpler substances by physical methods. They can be separated by chemical methods. Example of some compounds are water, ammonia, carbon dioxide, sugar, etc. The molecules of water and carbon dioxide are represented in figure 1.4. Note that a water molecule comprises 2 hydrogen and 1 oxygen atom. Similarly, a molecule of carbon dioxide contains 2 oxygen atoms combined with 1 carbon atom. Thus, the atoms of different elements are present in a compound in a fixed and definite ratio, and this ratio is characteristic of a particular compound. Also, the properties of a compound are different from those of its constituent elements. For example, hydrogen and oxygen are gases, whereas the compound formed by either their combination, that is water, is a liquid. It is interesting to note that hydrogen burns with a pop sound and oxygen is a supporter of combustion, but water is used as a fire extinguisher. 1.3 Properties of matter and their measurement. 1.3.1 Physical and chemical properties. Every substance has unique or characteristic properties. These properties can be classified into 2 categories: physical properties such as color, odor, melting point, boiling point, density, etc., and chemical properties like composition, combustibility, reactivity with acids and bases. Physical properties can be measured or observed without changing the identity or the composition of the substance. The measurement or observation of chemical properties requires a chemical change to occur. Measurement of physical properties does not require occurrence of a chemical change. The examples of chemical properties are characteristic reactions of different substances. These include acidity or basicity, combustibility, etc. Chemists describe, interpret, and predict the behavior of substances on the basis of knowledge their physical and chemical properties, which are determined by careful measurement and experimentation. In the following section, we will learn about the measurement of physical properties. 1.3.2 Measurement of physical properties. Quantitative measurement of properties is required for scientific investigation. Many properties of matter such as length, area, volume, etc. are quantitative in nature. Any quantitative observation of measurement is represented by a number followed by units in which it is measured. For example, length of a room can be represented as 6 meter. Here 6 is the number and m denotes meter, the unit in which the length is measured. Earlier, 2 different systems of measurement, that is the English system and the metric system, were being used in different parts of the world. The metric system, which originated in France in late 18th century, was more convenient as it was based on the decimal system. Late need of common standard system was felt by the scientific community. Such a system was established in 1960 and is discussed in detail below. 1.3.3 The International System of Units (SI). The International System of Units was established by the 11th General Conference on Weights and Measures (CGPM) from Conference General des Poids et Mesures. The CGPM is an intergovernmental treaty organization created by a diplomatic treaty known as Meter Convention, which was signed in Paris in 1875. The SI system has 7 base units and they are listed in table 1.1. These units pertain to the 7 fundamental scientific quantities. The other physical quantities such as speed, volume, density, etc. can be derived from these quantities. The definitions of the SI basic units are given in table 1.2. The SI system allows the use of prefixes to indicate the multiples or submultiples of a unit. These prefixes are listed in table 1.3. Let us now quickly go through the some quantities which you will be often using in this book. 1.3.4 Mass and weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by gravity on an object. The mass of a substance is constant, whereas its weight may vary from one place to another due to change in gravity. You should be careful in using these terms. The mass of a substance can be determined accurately in the laboratory by using an analytical balance. The SI unit of mass as given in table 1.1 is kilogram. However, its fraction named as gram, 1 kilogram is equals to 1000 gram, is used in laboratories due to the smaller amounts of chemical used in chemical reaction. 1.3.5 Volume. Volume is the amount of space occupied by a substance. It has the units of length to the power cube. So in SI system, volume has units of meter cube, but again in chemistry laboratories, smaller volumes are used, hence volume is often denoted in centimeter cube or decimeter cube units. A common unit liter, which is not an SI unit, is used for measurement of volume of liquids. 1 liter is equals to 1000 ml, 1000 centimeter cube is equals to 1 dm cube. In the laboratory, the volume of liquids or solution can be measured by graduated cylinder, burette, pipette, etc. A volumetric flask is used to prepare a known volume of a solution. These measuring devices are shown in figure 1.7. 1.3.6 Density. The two properties mass and volume discussed above are related as follows. Density is equals to mass upon volume. Density of a substance is its amount of mass per unit volume. So SI unit of density can be obtained as follows. SI unit of density is equals to SI unit of mass upon SI unit of volume. Kilogram per meter cube or kilogram meter to the power minus 3. This unit is quite large and a chemist often expresses density in gram centimeter cube, where mass is expressed in gram and volume is expressed in centimeter cube. Density of a substance tells us about how closely its particles are packed. If density is more, it means particles are more closely packed. Temperature. There are three common scales to measure temperature: degree Celsius, Fahrenheit and Kelvin. Here Kelvin is the SI unit. The thermometers based on these scales are shown in figure 1.8. Generally, the thermometer with Celsius scale are calibrated from 0 degree to 100 degree, where these two temperatures are the freezing point and the boiling point of water respectively. The Fahrenheit scale is represented between 32 degree to 212 degree Fahrenheit. The temperatures on two scales are related to each other by the following relationship. Fahrenheit is equals to 9 by 5 degrees Celsius plus 32. The Kelvin scale is related to Celsius scale as follows. Kelvin K is equals to degree Celsius plus 273.15. It is interesting to note that temperature below 0 degree Celsius are possible in Celsius scale, but in Kelvin scale, negative temperature is not possible. 1.4 Uncertainty in measurement. Many a time in the study of chemistry, one has to deal with experimental data as well as theoretical calculations. There are meaningful ways to handle the numbers conveniently and present the data realistically with certainty to the extent possible. These ideas are discussed below in detail. 1.4.1 Scientific Notation. As chemistry is the study of atoms and molecules which have extremely low masses and are present in extremely large numbers, a chemist has to deal with the numbers as large as 602, 200, 6 times 000 for the molecules of 2 gram of hydrogen gas, or as small as 0.23 times 0166 gram mass of hydrogen atom. Similarly, other constants such as Planck's constant, speed of light, charges on particles, etc. involve numbers of the above magnitude. It may look funny for a moment to write or count numbers involving so many zeros, but it offers a real challenge to do simple mathematical operations of addition, subtraction, multiplication or division with such numbers. You can write any two numbers of the above type and try any one of the operations you like to accept as challenge, and then you will really appreciate the difficulty in handling such numbers. This problem is solved by using scientific notation for such number, that is exponential notation, in which any number can be represented in the form n into 10 to the power n, where n is the exponent having positive or negative values and capital N is a number which varies between 1 to 9.999. Thus, we can write 232.508 as 2.32508 into 10 to the power 2 in scientific notation. Note that while writing it, the decimal had to be moved to the left by 2 places, and same is the exponent of 10 in the scientific notation. Similarly, 0.00016 can be written as 1.6 into 10 to the power minus 4. Here the decimal has to be moved 4 places to the right, and minus 4 is the exponent in the scientific notation. While performing mathematical operations on numbers expressed in the scientific notation, the following points are to be kept in mind: multiplication and division, addition and subtraction. 1.4.2 Significant figures. Every experimental measurement has some amount of uncertainty associated with it because of limitations of measuring instrument and the skill of the person making the measurement. For example, mass of an object is obtained using a platform balance and it comes out to be 9.4 gram. On measuring the mass of this object and an analytical balance, the mass obtained is 9.4213 gram. The mass obtained by an analytical balance is slightly higher than the mass obtained by using a platform balance. Therefore, digit 4 placed after decimal in the measurement by platform balance is uncertain. The uncertainty in the experimental or the calculated values is indicated by mentioning the number of significant figures. Significant figures are meaningful digits which are known with certainty plus 1, which is estimated or uncertain. The uncertainty is indicated by writing the certain digits and the last uncertain digit. Thus, if we write a result as 11.2 ml, we say that 11 is certain and 2 is uncertain, and thus uncertainty would be plus minus 1 in the last digit. Unless otherwise stated, an uncertainty of plus minus 1 in the last digit is always understood. There are certain rules for determining the number of significant figures. These are stated below. Number 1. All non-zero digits are significant. For example, in 285 cm there are 3 significant figures, and in 0.25 ml there are 2 significant figures. Number 2. Zeros preceding to first non-zero digit are non-significant. Such zero indicates the position of decimal point. The 0.03 has 1 significant figure and 0.0052 has 2 significant figures. Number 3. Zeros between the two non-zero digits are significant. Thus 2.005 has 4 significant figures. Number 4. Zeros at the end or right of a number are significant provided they are on the right side of the decimal point. Number 5. Counting the numbers of objects, for example 2 balls or 20 eggs, have infinite significant figures, as these are exact numbers and can be represented by writing infinite number of 0 after placing a decimal. In numbers written in scientific notation, all digits are significant. However, one would always like the results to be precise and accurate. Precision and accuracy are often referred to while we talk about the measurement. Precision refers to the closeness of various measurements for the same quantity. However, accuracy is the agreement of a particular value to the true value of the result. For example, if the true value for a result is 2 gram and student A takes 2 measurements and reports the result as 1.95 gram and 1.93 gram, these values are precise as they are close to each other but are not accurate. Another student B repeats the experiments and obtains 1.94 and 2.05 gram as the result for 2 measurements. These observations are neither precise nor accurate. Multiplication and division of significant figures. In these operations, the result must be reported with no more significant figures in the measurement with this few significant figures. While limiting the result to the required number of significant figures as done in the above mathematical operations, one has to keep in mind the following points for rounding off all the numbers. Number 1. If the rightmost digits to be removed is more than 5, the preceding number is increased by 1. If the rightmost digit to be removed is less than 5, the preceding number is not changed. If the rightmost digit is to be removed as 5, then the preceding number is not changed. If it is an even number but it is increased by 1 of its an odd number. 1.4.3 Dimensional analysis. Often while calculating, there is a need to convert units from one system to the other. The method used to accomplish this is called factor labeled method or unit factor method or dimensional analysis. This is illustrated below. 1.5 Laws of chemical combinations. The combination of elements to form compounds is governed by the following 5 basic laws. Number 1. Law of conservation of mass. This law was put forth by Antoine Lavoisier in 1789. He performed careful experimental studies for combustion reactions and reached to the conclusion that in all physical and chemical changes, there is no net change in mass during the process. Hence, he reached to the conclusion that matter can neither be created nor destroyed. This is called law of conservation of mass. This law formed the basis for several later developments in chemistry. In fact, this was the result of exact measurement of masses of reactants and products and carefully planned experiments performed by Lavoisier. 1.5.2 Law of definite proportion. This law was given by French chemist Joseph Proust. He stated that a given compound always contains exactly the same proportion of elements by weight. Proust worked with 2 samples of cupric carbonate, one of which was of natural origin and the other was synthetic. He found that the composition of elements present in it was same for both the samples as shown below. Thus, he concluded that irrespective of the source, a given compound always contains same elements combined together in the same proportion by mass. The validity of this law has been confirmed by various experiments. It is sometimes also referred to as law of definite composition. Third law, law of multiple proportions. This law was proposed by Dalton in 1803. According to this law, if two elements can combine to form more than one compound, the masses of one element that combine with the fixed mass of the other element are in the ratio of small whole numbers. For example, hydrogen combines with oxygen to form two compounds, namely water and hydrogen peroxide. Number 4. Gay-Lussac's law of gaseous volume. This law was given by Gay-Lussac in 1808. He observed that when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume, provided all gases are at the same temperature and pressure. Thus, 100 ml of hydrogen combined with 50 ml of oxygen to give 100 ml of water vapor. Thus, the volumes of hydrogen and oxygen which combine bear a simple ratio of 2:1. Gay-Lussac's discovery of integer ratio in volume relationship is actually the law of definite proportions by volume. The law of definite proportions stated earlier was with respect to mass. The Gay-Lussac law was explained properly by the work of Avogadro in 1811. 1.5.5 Law, Avogadro's law. Fifth law, Avogadro's law. In 1811, Avogadro proposed that equal volumes of all gases at the same temperature and pressure should contain equal number of molecules. Avogadro made a distinction between atoms and molecules, which is quite understandable in present times. If we consider again the reaction of hydrogen and oxygen to produce water, we see that two volumes of hydrogen combine with one volume of oxygen to give two volumes of water without leaving any unreacted oxygen. Note that in the figure 1.9, page 16, each box contains equal number of molecules. In fact, Avogadro could explain the above result by considering the molecules to be polyatomic. If hydrogen and oxygen were considered as diatomic as recognized now, then the above results are easily understandable. However, Dalton and others believed that atoms of the same kind cannot combine and molecules of the oxygen or hydrogen containing two atoms did not exist. Avogadro's proposal was published in the French journal De Physique. In spite of being correct, it did not gain much support. After about 50 years, in 1860, the first international conference on chemistry was held in Karlsruhe, Germany, to resolve various ideas. At the meeting, Stanislaw Cannizzaro presented a sketch of course of chemical philosophy which emphasized on the importance of Avogadro's work. 1.6 Dalton's atomic theory. Although the origin of the idea that matters is composed of small indivisible particles called atomio dates back to the time of Democritus, a Greek philosopher, it again started emerging as a result of several experimental studies which led to the laws mentioned above. In 1808, Dalton published a new system of chemical philosophy in which he proposed the following. Number 1. Matter consists of indivisible atoms. Number 2. All atoms of given element have identical properties including identical mass. Atoms of different elements differ in mass. Number 3. Compounds are formed when atoms of different elements combine in a fixed ratio. Number 4. Chemical reactions involve reorganization of atoms. These are neither created nor destroyed in a chemical reaction. Dalton's theory could explain the laws of chemical combination. However, it could not explain the laws of gaseous volumes. It could not provide the reason for combining of atoms, which was answered later by other scientists. 1.7 Atomic and molecular masses. After having some idea about the terms atoms and molecules, it is appropriate here to understand what do we mean by atomic and molecular masses. 1.7.1 Atomic mass. The atomic mass or the mass of an atom is actually very small because atoms are extremely small. Today we have sophisticated techniques, example mass spectrometry, for determining the atomic masses fairly accurately. But in the 19th century, scientists could determine the mass of one atom relative to another by experimental means, as has been mentioned earlier. Hydrogen, being the lightest atom, was arbitrarily assigned a mass of 1 and other elements were assigned masses related to it. However, the present system of atomic masses is based on carbon-12 as the standard and has been agreed upon in 1961. Here, carbon-12 is one of the isotope of carbon and can be represented as 12 carbon in the system. 12 carbon is assigned as mass of exactly 12 atomic mass unit EMU, and masses of all other atoms are given relative to this standard. One atomic mass unit is defined as a mass exactly equal to 1/12 of the mass of one carbon-12 atom. At present, AMU has been replaced by U, which is known as unified mass. When we use atomic masses of elements in calculations, we actually use average atomic masses of elements, which are explained below. 1.7.2 Average atomic mass. Many naturally occurring elements exist as more than one isotope. When we take into account the existence of these isotopes and their relative abundance, the average atomic mass of that element can be computed. For example, carbon has the following three isotopes with relative abundances and masses as shown against. Similarly, average atomic masses for other elements can be calculated in the periodic table of elements. The atomic masses mentioned for different elements actually represent their average atomic masses. 1.7.3 Molecular mass. Molecular mass is the sum of atomic masses of the elements present in a molecule. It is obtained by multiplying the atomic mass of each element by the number of its atoms and adding them together. For example, molecular mass of methane, which contains one carbon atom and 4 hydrogen atoms, can be obtained as follows. Molecular mass of methane is equals to 16.043 U. 1.7.4 Formula mass. Some substances such as sodium chloride do not contain discrete molecules as their constituent units. In such compounds, positive and negative entities are arranged in a three-dimensional structure as shown in figure 1.10. It may be noted that in sodium chloride, one Na ion is surrounded by 6 chloride ion and vice versa. The formula such as NaCl is used to calculate the formula mass instead of molecular mass, as in the solid state sodium chloride does not exist as single entity. Thus, the formula mass of sodium chloride is atomic mass of sodium plus atomic mass of chlorine, that is 58.5 U. 1.8 Mole concept and molar mass. Atoms and molecules are extremely small in size, and their numbers in even a small amount of any substance is really very large. To handle such large numbers, a unit of convenient magnitude is required. Just as we denote 1 dozen for 12 items, score for 20 items, gross for 144 items, we use the idea of mole to count entities at the microscopic level. In a SI system, mole was introduced as 7th base quantity for the amount of a substance. The mole symbol mol is the SI unit of amount of substance. One mole contains exactly 6.022140076 into 10 to the power 23 elementary entities. This number is the fixed numerical value of the Avogadro constant Na, when expressed in the unit mole to the power -1, and is called the Avogadro number. The amount of substance symbol N of a system is a measure of the number of specified elementary entities. An elementary entity may be an atom, a molecule, an ion, an electron, any other particle, or a specified group of particles. It may be emphasized that the mole of a substance always contains the same number of entities, no matter what the substance may be. In order to determine this number precisely, the mass of carbon-12 atom was determined by a mass spectrometer and found to be equal to 1.992648 into 10 to the power -23 gram. Knowing that 1 mole of carbon weighs 12 gram, the number of 12 atoms in it is equal to 12 gram per mole. This number of entities in 1 mole is so important that it is given a separate name and symbol. It is called Avogadro constant or Avogadro number, denoted by Na in honor of Amedeo Avogadro. To appreciate the largeness of this number, let us write it with all zeros without using any powers of 10. Having defined the mole, it is easier to know the mass of 1 mole of a substance or the other constituent entities. The mass of 1 mole of substance in grams is called its molar mass. The molar mass in grams is numerically equal to atomic molecular formula mass in U. Molar mass of water 18.02 gram per mole. Molar mass of sodium chloride 58.5 gram per mole. 1.9 Percentage composition. So far we were dealing with the number of entities present in a given sample, but many a time information regarding the percentage of a particular element present in a compound is required. Suppose an unknown or new compound is given to you. The first question you would ask, what is its formula, or what are its constituents and what ratio are they present in the given compound? For known compounds also, such information provides a check whether the given sample contains the same percentage of elements as present in a pure sample. In other words, one can check the purity of given sample by analyzing this data. Let us understand it by taking the example of water. Since water contains hydrogen and oxygen, the percentage composition of both these elements can be calculated as follows. Mass percentage of an element is equals to mass of that element in the compound into 100 upon molar mass of the compound. 1.9.1 Empirical formula for molecular formula. An empirical formula represents the simplest whole number ratio of various atoms present in a compound, whereas the molecular formula shows the exact number of different types of atoms present in a molecule of a compound. If the mass percent of various elements present in a compound is known, its empirical formula can be determined. Molecular formula can further be obtained if the molar mass is known. The following example illustrates this sequence. 1.10 Stoichiometric and stoichiometry calculations. The word stoichiometry is derived from two Greek words, stoichion and metron. Stoichiometry thus deals with the calculation of masses of the reactants and the products involved in a chemical reaction. Before understanding how to calculate the amounts of reactants required or the products produced in a chemical reaction, let us study what information is available from the balanced chemical equation of a given reaction. Let us consider the combustion of methane. A balanced equation for this reaction is as given below. CH4 plus 2O2 gives out CO2 plus 2H2O. Here methane and dioxygen are called reactants and carbon dioxide and water are called products. Note that all the reactants and the products are gases in the above reaction, and this has been indicated by letter in the brackets next to its formula. Similarly, in case of solids and liquids and are written S and L respectively. Thus, according to the above chemical reaction, 1 mole of CH4 reacts with 2 moles of O2 to give 1 mole of CO2 and 2 moles of H2O. 1 molecule of CH4 reacts with 2 molecules of O2 to give 1 molecule of CO2 and 2 molecules of H2O. Calculations you have to check from your book. 1.10 Limiting reagent. Many a time reactions are carried out with the amounts of reactants that are different than the amounts as required by a balanced chemical reaction. In such situations, one reactant is in more amount than the amount required by a balanced chemical reaction. The reactant which is present in the least amount gets consumed after some time, and after that further reaction does not take place, whatever be the amount of the other reactant. Hence, the reactant which gets consumed first limits the amount of products formed and is therefore called limiting reagent. In performing stoichiometric calculation, this aspect is also to be kept in mind. 1.10.2 Reactions in solutions. A majority of reactions in the laboratories are carried out in solution. Therefore, it is important to understand as how the amount of substance is expressed when it is present in the solution. The concentration of solution or the amount of substance present in its given volume can be expressed in any of the following ways. Number 1. Mass percent or weight percent. Mole fraction, molarity, molality. Let us now study each one of them in detail. Balancing a chemical equation you have to check from your book. All the examples you have to check from your book. Number 1, mass percent. It is obtained by using the following reaction. Mass percent is equals to mass of solute upon mass of solution into 100. Number 2, mole fraction. It is the ratio of number of moles of a particular component to the total number of moles of the solution. If a substance A dissolves in a substance B and their number of moles are Na and Nb respectively, then the mole fractions of A and B are given as mole fraction of A is equals to number of moles of A, number of moles upon number of moles of solution. Mole fraction of B is equals to number of moles of B upon number of moles of solutions. Number 3, molarity. It is the most widely used unit and is denoted by capital M. It is defined as the number of moles of the solute in 1 liter of the solution. Thus, molarity is equals to number of moles of solute upon volume of solutions in liter. Number 4, molality. It is defined as the number of moles of solute present in 1 kg of solvent. It is denoted by small m. Thus, molality is equals to number of moles of solute upon mass of solvent in kg. Summary. Chemistry as we understand it today that it is not a very old discipline. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied the knowledge in various walks of life. The study of chemistry is very important as its domain encompasses every sphere of life. Chemists study the properties and structure of substances and the changes undergone by them. All substances contain matter which can exist in 3 states, solid, liquid or gas. The constituent particles are held in different ways in these states of matter and they exhibit their characteristic properties. Matter can also be classified into elements, compounds or mixtures. An element contains particles of only one type, which may be atoms or molecules. The compounds are formed where atoms of 2 or more elements combine in a fixed ratio to each other. Mixtures occur widely, and many of the substances present around us are mixtures. When the properties of a substance are studied, this measurement is inherent. The quantification of properties requires a system of measurement and units in which the quantities are to be expressed. Many systems of measurement exist, of which the English and the metric systems are widely used. The scientific community, however, has agreed to have a uniform common system throughout the world, which is abbreviated as a SI unit, International System of Units. Since measurements involve recording of data, which are always associated with a certain amount of uncertainty, the proper handling of data obtained by measuring the quantities is very important. The measurements of quantities in chemistry are spread over a wide range of 10 to the power minus 31 to 10 to the power plus 23. Hence, a convenient system of expressing the numbers in scientific notation is used. The uncertainty is taken care by specifying the number of significant figures in which the observations are reported. The dimensional analysis helps to express the measured quantities in different systems of units. Hence, it is possible to interconvert the results from one system of units to another. The combination of different atoms is governed by basic laws of chemical combination, these being the law of conservation of mass, law of definite proportion. The combination of different atoms is governed by basic laws of chemical combination, these being the law of conservation of mass, law of definite proportions, law of multiple proportions, Galois laws of gaseous volumes and Avogadro law. All these laws led to the Dalton's atomic theory, which states that atoms are building blocks of matter. The atomic mass of an element is expressed relative to 12 carbon isotope of carbon, which has an extinct value of 12U. Usually, the atomic mass used for an element is the average atomic mass obtained by taking into account the natural abundance of different isotopes of that element. The molecular mass of a molecule is obtained by taking sum of the atomic masses of different atoms present in a molecule. The molecular formula can be calculated by determining the mass percent of different elements present in a compound and its molecular mass. The numbers of atoms, molecules or any other particles present in a given system are expressed in the terms of Avogadro constant 6.022 into 10 to the power 23. This is known as 1 mole, the respective particles or entities. Chemical reactions represent the chemical changes undergone by different elements and compounds. A balanced chemical equation provides a lots of information. The coefficient indicate the molar ratios and the respective number of particles taking part in a particular reaction. The quantitative study of the reactants required or the products formed is called stoichiometry. Using stoichiometric calculations, the amount of one or more reactant required to produce a particular amount of product can be determined and vice versa. The amount of substance present in a given volume of a solution is expressed in a number of ways. Example, mass percent, mole fraction, molarity and molality. Chapter completed. Thank you so much.